Let's look at an example of estimating distance using left sums and right sums. Suppose a Mars lander is traversing the Martian landscape taking samples, and you are interested in determining how far it has traveled during a certain time interval. Suppose that the lander sends back data every 15 minutes, and one of the pieces of information it sends back is the current speed, in, let's say, meters per hour. Suppose over the course of a given 2-hour period, the speed was reported at each 15-minute interval and compiled into the table you see here. What we want to do is estimate the distance traveled between 5 o'clock and 7 o'clock using the information provided. We'll use left sums and right sums to do this estimation. In the graph you see here, we've plotted velocity versus time. Time is given in minutes. It's minutes since 5 o'clock. So we start at t equals 0, and that's at 5 o'clock. The velocity is in meters per hour. So at some point we're going to need to convert our time from minutes to hours in order to do the computations. Our graph is a series of points because we don't actually have a continuous curve giving us velocity at time because we weren't given that much information. We were only given a single number every 15 minutes. There must be some continuous curve connecting these points, but we don't know what it is. We can just simply assume that it's something very natural, something connecting these points like so. Now, we don't actually know that that's the case. All we know is that the curve passes through these points, but it could do so quite wildly like that. Now, there's no reason to assume that it does that. So since no additional information is there to tell us otherwise, we can just assume that the curve looks something like this. What we want to do is approximate the distance traveled. We want to approximate the distance or the area under the curve, since those are the same thing. The first thing we want to try is we want to try using left-hand sums. That is the left endpoint approximation. So let's put an L there for the left endpoint approximation. Notice how many intervals there are. There's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 intervals altogether, and so we're going to have a sum with 8 terms. What is our delta t in this case? Delta t is 15 minutes, but we're going to measure everything in hours, so that's 1/4 of an hour. So let's keep that in mind. Each one of these rectangles here, or one of these squares, then, is 1/4 of an hour, and so on. So all of our rectangles are going to have bases that are length 1/4. Now what about the height? The height is determined by the left endpoint in this case. So for each interval, you construct a rectangle. And the height of the rectangle is determined by the left endpoint. So for the first rectangle, it's going to be height 15. And for the second rectangle, it's going to be height 25, like so. The third rectangle has base between 30 and 45 minutes after 5 o'clock. So again, you use the left endpoint. Notice now that it's going over. It was underneath, but now it's over. The heights of these are all determined by the numbers that appear in this chart. The first one is 15, the second one is 25, and the third one is 32, and the fourth one would be 26, and so on and so forth. So that means the heights are given to us in that table. So we can simply write these down. It's going to be 15 times 1/4 plus 25 times 1/4 plus 32 times 1/4 and so on. Now we can actually take out the 1/4 and that might make things a little bit easier. So let's factor that out. So it's going to be 1/4 times 15 plus 25 plus 32 plus, and I just simply keep going along this table until I get to the last interval. Now the last interval is here, And if I'm using the left sum, I use the left endpoint, and so I get a rectangle like this. The height of this rectangle is 28. So I just have to add up all of these terms, starting at 15 until I get to 28. I don't include 31 because the 31 belongs to the right endpoint. So if we're going to do R8 later, then our last sum will involve the 31. But for now, we just go up until we get to 28. So it's 15 plus 25 plus 32 plus 26 plus 17 plus 14 plus 20 plus 28. And if you do a little bit of computation, you should get that this will end up being 44.25. So our left approximation tells us that our Mars lander has traveled approximately 44.25 meters. We can now do the right endpoint, R8. We can use the right endpoints to get the right endpoint sum, or the right endpoint approximation. In this case, let's change the color. In this case, for each interval, we want to use not the left endpoint, but the right endpoint. So the first one looks something like this. Notice that this rectangle was actually in the previous computation as well as our second rectangle. Basically what's happening is all of the rectangles are going to get moved over to the left by one, like that. So all of the rectangles just move over one. And at the very end, we'll be using the right endpoint. So instead of going up to 28, we're going to go up to 31. 31. So now we're not using 15, we're starting at 25. So now we start here at 25, and we go until we get to 31. So let's just add all of those things together. So again, the length is still 1/4 of an hour, but now it's 25 plus 32 plus 26 plus 17 plus 14 plus 20 plus 28, and we need one more, which is 31. The 28 comes from the second to last interval, which is here. Again, that rectangle appeared in the previous, but now it got moved over one. And if you do your computations and add this up, this should end up being 48.25. These are our two approximations. Now, neither one of these would we expect to be the exact distance traveled, but both of these should be a close approximation. We also shouldn't assume that the actual distance traveled is between 44.25 and 48.25. There's no reason to assume that the left endpoint sums are a lower or underestimate, and the right endpoint sums are an upper estimate. There's no reason to assume that that's true. If we want to get some better idea of what an upper and lower estimate are, we should look at our graph again. So here's our graph again. Well, the points, again, we can imagine that the curve passes through these points, like so. We don't actually know that, but let's just assume for the sake of argument that it looks something like that. Now, if I wanted to find an upper estimate, then I shouldn't look just at the left endpoints or the right endpoints. On each interval, I should always choose the maximum to give me the height of my rectangle. So for example, on my first interval here, which is from 0 to 15 minutes, I see that this is an increasing function. So I should choose the right endpoint to give me the height of my rectangle. Similarly, between 15 and 30 minutes after 5 o'clock, I'm still increasing, so I choose the right endpoint to determine the height of my second rectangle, like so. However, if I want an upper estimate upper estimate or an upper bound, I need to make sure that my rectangles are always above the curve. So between 30 and 45 minutes after 5 o'clock, I have a decreasing function. So now what I do is I don't choose the right endpoint, I choose the left endpoint. Remember, my goal is to get an overestimate. So I need to make sure that my rectangles are above the curve. Now between 45 and 60, I do the same thing. I choose the left endpoint, like this. Between 60 and 75, again, the function is decreasing, so I choose the left endpoint. But now the function is increasing, so I switch and I choose the right endpoint. The goal is to always pick the maximum value for my height of my rectangle. And after this point, the function continues increasing, so I always choose the right endpoint, like this. So in each case, I need to choose the maximum, the highest value. So our upper estimate will be a sum, and again it will be 1/4 times, and now I have to pick I have to pick out the heights of these rectangles. So the first one is 25, and then the second one, if I can't remember the number, I go back to the table, is 32. So this height right here is at 32. And notice there are two of them. So it's 32 plus 32 plus, and then the next one is going to be 26. That's this one. And then the next one is going to be at 60, and the 60 is 17. And then the next one is at 90 minutes after. So at 90 minutes, that's an hour and a half, so we're at 6:30, that's going to be 20. And then we pick 28 and 31. And this is going to be our upper estimate. And I believe if you do that computation, you end up with 53. So that tells us that whatever our distance traveled is, it should be below 53, assuming that the curve looks something like what we have here and not something completely erratic. If you wanted to do a lower estimate, you would do something similar, but for a lower estimate, you always pick the smallest height available. So on your first interval, that will happen at 15, like this. And then for your second interval, you'll pick the smaller endpoint, or the height at the left endpoint, because that's smaller. And that gives you your second rectangle. Your third rectangle between 30 and 45 minutes, again, you're looking for an underestimate, so you want to choose the smallest value, which is right here at 26, like that. And so on and so forth. You just always pick the smallest to ensure that the rectangle is completely underneath the curve, like that. And that will give you a lower estimate. If you work this out, this will be 1/4 times, and now it'll be 15 plus 25 plus 26 plus, and now we need to find the height at 60, which I think we did before, and we saw that that was 60 minutes, of course, is an hour after, so that's 17. So that's going to be 17 plus, and then we want another 15, or 14 rather. So this height is 14. So plus 14, plus 14, plus, and then I believe it's a 20, and finally we're going to have a 28. And if you do these computations, I believe you get 39.75. So these are our upper and lower estimates. So whatever the actual distance traveled, whatever the area is under the curve, we can be reasonably certain, given the information that we have here, that the actual distance is bigger than 39.75 and smaller than 53.